A linear time invariant is modeled by a vector matrix differential equation. Dx over dt is bx, where b is the matrix 0, 1, negative 2, 3. Then you've been told to determine the state transition matrix and the state transition matrix at time t is equals to 0. Now the first thing, when you are given a differential equation, dx over dt to be equals to bx, we can use the method of separation of variables, where we will have that will be the same as dx over x, that will be dx over x to be equals to b dt. So if you integrate both sides, if you integrate dx over x, you integrate both sides, you introduce the integral on both sides of the equation, you'll find the integral of dx over x is ln of x to be equals to, then if you integrate b dt, you'll get bt plus the arbitrary integration constant c. Now, ln is the inverse of exponential function. If you introduce exponent on both sides of the equation, if we introduce exponent on both sides of the equation, here we have ln of x to be that, then what will we get? We'll get exponential raised to power ln of x to be the same as exponential raised to power bt plus c. Now, exponential raised to power bt plus c, when you start from the left hand side of the equation, exponential ln of x is just x to be equals to, then if you use the laws of indices, exponential bt plus c will be exponential bt times exponential raised to power c. Now, this is the solution of the differential equation x being a function of t. So here, this is now what is equivalent to the phi invariant. This is what is equivalent to the phi invariant times exponential raised to power c. So when you are told to find the state transition matrix, the state transition matrix, you can see it is the exponential bt, which is the same as the state transition. So it's the state transition matrix. So in other words, we are saying when you are given matrix B, the way we've been given here, when you are given matrix B to be equals to that, then the transition matrix phi variant of t, the transition matrix phi variant of t will be given by exponential bt. So when you are told to find the transition matrix, then you simply equate that. So what do they want? They want you to solve this equation. They want you to solve this equation, phi invariant of t to be equals to exponential bt. So you've actually seen how that transition matrix is coming about. Now remember, we want to solve this problem without using Laplace transform. The simplest method to solve this, we can solve it actually without using Laplace transform. When you have matrix B, by definition of eigenvectors and eigenvalue, if you are given a transition matrix B, if you have matrix B, is always equals to P inverse. That is how matrix B is defined. Where P is the matrix of eigenvectors, and D is the diagonal matrix of eigenvalues. values is the diagonal matrix of eigenvalues. That means, so the moment when you have matrix B, if you have matrix B to be equals to PDP inverse, then exponential BT. Now here, when you take this definition, it was proven that the exponential of BT, exponential raised to power BT, is going to be P exponential of DT. That is how to define. And you can see exponential BT is the state transition matrix. So it means anytime you are told to find the state transition matrix, the phi variant, if you are told to find the state transition matrix, the phi variant of a function, which is a function of t, is the same as exponential BT, which is equals to P exponential exponential dt, then times the P inverse. Now, how do we get? We will first start by getting this matrix exponential, this matrix of the exponential d, exponential d dt. How do we define this matrix exponential dt? Now, this matrix exponential dt is normally given by, if you have the matrix exponential dt, it is normally given by the exponential lambda 1. If you have exponential lambda 1 t 0, then here we'll now have exponential lambda 2 t. That means this is the implication. The implication say if lambda 1 if lambda 1 and lambda 2 are eigenvalues, if lambda 1 and lambda 2 are eigenvalues, then the diagonal matrix D is given by, lambda 1, lambda 2. It is a diagonal matrix because there are only elements along the main diagonals and 0 elsewhere. Then diagonal matrix D is given by that. So from there you can now see the implication from that our first case there. What is the implication? The implication is that this is the implication you can now make. You can say if D is equals to the diagonal matrix of lambda 1, lambda 2, then exponential dt. Then exponential dt is given by exponential lambda 1 t 0 0 exponential lambda 2 along, that is also the diagonal matrix. So for us to solve this problem, for us to get the transition matrix, the phi invariant, which is a function of t, for us to get this transition matrix, then it means we will only have to get the eigenvalues and the corresponding eigenvectors. We will have to find the eigenvalues and the corresponding eigenvectors. So we go and we start with our matrix B. So we start with the matrix B. If you are given matrix B to be this, if this is matrix B, then minus lambda I, V minus lambda I, V minus lambda I, where I is the identity matrix, the determinant of B minus lambda I is equals to 0 for you to get the corresponding, to get the eigenvalues of that matrix. And that one is normally given by, if you work out that, you will find it is just lambda squared minus trace lambda squared minus trace lambda plus determinant to be equals to 0. So it means for us to solve this equation, all we need, if you look at this equation, you'll actually see this is an auxiliary equation. It is an auxiliary equation. And in an auxiliary equation, what do you know about an auxiliary equation? In an auxiliary equation, when you have two real solutions, when you get two real solutions, so the moment you are going to get two real solutions, what does that imply? When you get two real solutions of an auxiliary equation, then it means the method of undetermined coefficients, you will have the solution to be what? To be the two real solutions, lambda 1 and lambda 2. Then you will get the solution to be in which form? You will get the solution to be in the form A exponential, the first, maybe you can use capital A for that, constant, exponential, the first real solution, which is the lambda 1. So the first real solution there will be lambda 1, A lambda 1, t, because it was a function of t, then plus B exponential, lambda 2, t. You can remember in the method of undetermined coefficients, when you had two real solutions, this was the general solutions of the homogeneous second order ordinary differential equation. When we are now taking this to be the auxiliary equation, if you take this to be the auxiliary equation, meaning this will be the general equation, meaning when you transform this in form of a matrix, then you'll get what? You'll get it is the matrix of, you'll get it is the 2 by 2 matrix of the exponential function, exponential lambda 1 t 0 0, then exponential lambda 2t, then it is times the matrix, A 0 0 b. So you can see first row times first column, you'll get this term, and second row and second term, you will always get this term. So you can see how this matrix was coming about. This matrix of the diagonal matrix exponential dt. You can see how we were defining such kind of matrix. So this matrix, we'll get it by dealing with a case of an auxiliary equation in the method of undetermined coefficients. So we now go back to our problem. We said when you have b to be this, then lambda squared minus trace lambda plus d is equals to 0. Remember, trace is the sum of the elements in the main diagonal. Trace is the sum of the elements in the main diagonal. So if you are looking for t, the trace, you add up the elements in the main diagonal. The elements in the main diagonal is 0. We have this 0 plus negative 3. Trace is the sum of the elements in the main diagonal. Main diagonal, we have 0 and negative 3. So you'll get the trace to be negative 3. Then after that, you get the determinant. The d is the product of the elements in the main diagonal. That will be 0 times negative 3. That is 0 times negative 3 is the product of the elements in the main diagonal. Then minus product of the elements in the other diagonal. That is negative 2 times 1. So if you work out that, what you get to be d will be 0 minus negative 2. You get the value there is 2. So if you substitute back that into your equation, this is your equation. So in this your equation, where there is trace, you put the value, whatever you are substituting, you put in bracket. We want to substitute the value of t and the value of d. So the value of t trace we found is negative 3. And the value of d determinant we found is 2. So if you simplify that equation, you will get lambda squared plus 3. Remember, negative into negative 3 is plus 3 lambda. Plus 3 lambda plus 2 is equals to 0. Now, if you solve this equation, you can see this is a quadratic equation. What will be the solution of lambda? Lambda will be equals to minus b plus or minus square root of b squared minus 4ac over 2a. So here you can see our value of a is 1. So where there is a, you substitute the value of a. We are going to substitute the value of a, the value of c, the value of b. Anywhere you see the unknown, you substitute their values. The value. So you can see a is the coefficient of lambda squared, meaning the coefficient of lambda squared there is 1. So 1 is the value of a, the coefficient of lambda squared. So anywhere you see a, you put the value of a. So we've seen a is 1. Where there is a, you put the value of a is 1. Then b is the coefficient of lambda, that is positive 3. So anywhere you see b, you put the value of b, that is positive 3. Then where there is c is positive 2, you put the value of c, that is positive 2. So if you simplify this, what will you get? If you simplify this in the numerator, we will have negative 3 plus or minus square root of 3 squared. 3 squared is 9 minus 4 times 1 times 2 is 8 over 2 times 1 is 2. So remember, 9 minus 8 is 1. Then square root of 1 is 1. So these are the two solutions of lambda. So these two solutions of lambda will give us the two values of lambda, lambda 1 and lambda 2. So we have the two solutions there. The first one, solution is lambda 1 will be equals to what? This is the solution of lambda. Lambda 1 is equals to this. So when we want this, we block one sign. If we block negative sign, we will remain with positive in the middle. So negative 3 plus 1 is negative 2 divided by 2. Then you get the solution of the first lambda there to be 1. Then the second solution, lambda 2, the second solution you will have there lambda 2 to be equals to, you take back the solution of lambda was this, lambda 2 will be what? So the first case we blocked the positive, we blocked the negative. Now when we block the positive, we remain with the negative. So we'll get negative 3 minus 1, that is negative 4 over 2. So you get the solution of lambda 2 is what? Is negative 2. So we found the two solutions of lambda. So we found two real solutions. So we found two real solutions. So when you have two real solutions, then it means the general solution is going to be in the what form? It's going to be in the form of a constant. When we have two real solutions, then it means our matrix D, let us just, because we've already defined it here, when you have two real solutions, you will get this to be the general solution, which would have been this form in case of a matrix. So what is our matrix D? If you go back, you see if D is lambda 1 is a diagonal matrix, then exponential dt is given by that. So it means we found the diagonal matrix D. This diagonal matrix D here, this definition, you can remember if D is given by lambda 1, lambda 2, then exponential dt is given by this. So you substitute the values of lambda. So lambda 1 we found is negative 1. So it means where you see lambda 1, you put negative 1. Where you have lambda 1, you put negative 1. Then lambda 2 we found is negative 2. So where you see lambda 2, you put negative 2. Lambda 2 we found is negative 2. So we found the diagonal matrix D and exponential dt. Now what is left is now to get what? The matrix of the eigenvectors, matrix P. So matrix P will be the matrix of eigenvectors. So we want to get the eigenvectors. So you start when lambda 1 is, we found lambda 1 is negative 1. We want to get the corresponding eigenvector. So what happens? Remember, the corresponding eigenvector is given as Bx is equals to what? Is equals to lambda x, where x is the eigenvector. So that x eigenvector, we can define it as the eigenvector x, we can define it as x1 as x1, x2. So that is the eigenvector. So if we substitute in this equation here, we have this equation. If we do the substitution, what will we get? We will get where there is B, we put matrix B. And what is our matrix B? When you go back, where is matrix B? Matrix B was this, that was matrix B. So you go and you substitute matrix B, where there is B, you put matrix B. Then where there is X, you put that eigenvector. You've defined it here as X1, X2. Then where there is lambda, we are going to put the lambda values. Then X is that, defined like that. So start the first case with the lambda 1. When you have this lambda 1. So the solution for lambda 1, when lambda 1 is equals to negative 1. So when lambda 1 is equals to negative 1, it means in this equation, where there is lambda, we are going to put negative 1. So what do you know? The scalar multiplies all the elements of a matrix. So this negative 1, if you take it inside, it is a scalar. This negative 1, it will multiply all the elements. So we'll have negative x1, negative x2, because negative 1 times x1 is negative x1, negative 1 times x2 is negative x2. So you start multiplication. So here, what do we have here? We are going to multiply first row times, we are going to have the first row times the first column. What do you get there? First row times the first column. If you multiply that, what do you get? So there we are going to get our matrix. First row times first column will be an element of the first row first, will be an element of the first row first column. If you multiply that, you get to be equals to, so you can see 0 times x1 is 0, then plus 1 times x2 is just going to be what? Is going to be x2. So there we have 0 plus x2. Then we go back to the next one, second row times first column. What will you get? Negative 2 times x1. We will get negative 2x, negative 2x1. That will be negative 2x1. Then negative 3 times x2 is going to be negative 3x2 to be equals to what? On the other side of the equation, we have x negative x1, negative x2. So on the other side of the equation, we have negative x1 and negative x2, like that. So that is what we have. Now from there, we now start comparing. The first equation, 0 plus x2, will imply what? It will imply x2 is equals to what? Negative x1. So x2 is equals to negative value of x1. So if you let x1 to be a unit, if you let this x1 to be 1, then what is x2? Then you have x2 is what? Then you'll have x2 to be equals to negative of x1, but x1 is 1. So x2 will be negative 1. So what do you conclude? So in conclusion, we can see when lambda 1 is equals to 1 here, when you have lambda 1 to be equals to 1, negative 1, when lambda 1 is equals to negative 1, then the corresponding eigenvector x is going to be what? The eigenvector x was, the eigenvector x you said was given by this, x1, x2. Then the corresponding eigenvector x1, x2 will be what? Will be equals to this. Where there is x1, you put the value of x1, x1 is 1. So where there is x1, you substitute the value of x1, then x2 is negative 1. Where there is x2, you put the value of x2, negative x1. So we have found the corresponding eigenvector when eigenvalue lambda 1 is negative 1. You can repeat now the same process from here onwards. The whole of this, you can repeat the same process with the lambda 2, meaning you go back when lambda 2 was negative 2. So instead of lambda 1, we now want, this is now when lambda 2 is equals to negative 2. So it means where there's lambda 2, we will put negative 2. So negative 2 multiplies everything. Inside the bracket, you get negative 2x1, negative 2x2. So if you multiply this side of the equation, will remain the way it was. Then here we have negative 2x1, negative 2x2. So you can see here, x2 is equals to negative 2x1. Using that, so that when x1 is 1, then x2 is negative 2 into 1. So you'll get x2 is negative 2. So this is when lambda 2 was negative 2, then x1, then the corresponding eigenvector x1 you've seen is 1, then x2 we found is now negative 2. Since we've did it, so we've seen when lambda 2 is negative 2, the corresponding eigenvector is 1, negative 2. So once you found that, we can now get matrix P, the matrix of eigenvectors. So matrix P, the matrix of eigenvectors, will be given by what? So here, matrix P will be, remember, lambda 1, if you go back here, lambda 1 was occupying the first row column. So it means the eigenvector for lambda 1 must be in the first column, because lambda 1 was occupying the first column. So the eigenvector of lambda 1 must be in the first column. And what is the eigenvector of lambda 1? It is 1, negative 1. So it means the first column, we are going to have 1, negative 1, because lambda 1 was in the first column. Then lambda 2, which was in the second column, will now, the corresponding eigenvector will occupy the second column, and that corresponding eigenvector is 1, negative 2. So there we'll have 1, negative 2. So put the vectors in a column form. So this is V1, V2 in that order. So once you get matrix P, you can now get the inverse of matrix P. So the inverse of matrix P, that is P inverse, is given by what? 1 over determinant of P into the matrix P. How do we get the inverse of a 2 by 2 matrix? You interchange the elements in the main diagonal. So the main diagonal, we have 1 and negative 2. So when we interchange, we'll have negative 2 and 1. Then you change the sign of the elements in the other diagonal. Here we have positive 1. If we change the sign, it now becomes negative 1. Then here we have negative 1. If we interchange the sign, it becomes positive 1. So what we need to get is the determinant of matrix P. The determinant of matrix P is the product of the elements in the main diagonal. That is 1 times negative 2. That is 1 times negative 2 minus the product of the elements in the other diagonal, which is negative 1 times 1. That is negative 1 times 1. So if you multiply this, 1 times negative 2, you will get the whole of this will be negative 2. Then when you multiply 1 times negative 1, that will be negative 1. So negative 2 minus negative 1 is like negative 2 plus 1. So negative 2 plus 1 is going to be negative 1. So when you have 1 over negative 1, that is negative 1. So negative 1 will multiply all the elements inside the bracket. So we will have the matrix there, the 2 by 2 matrix there. So negative 1 times negative 2, you get 2. Negative 1 times negative 1, you get 1. Then negative 1 times 1, you get negative 1. Then negative 1 times 1, you get negative 1. Now, we found matrix P. What we were interested in is getting matrix P inverse, and getting exponential, dt. We also found exponential dt to be this. So we found exponential dt to that. So we found everything. We found the matrix P of the eigenvectors and its inverse at exponential dt. So for you now to get the transition matrix, you go back. You see, the transition matrix you had by definition is what? The equivariant of t is given by exponential bt. So the transition matrix we are looking for is P exponential dt P inverse. So if you substitute the values, what will you have? That will be equals to, where there is P, you put the value of P. So P we found to be this. We are doing substitution. Order of a matrix must be maintained. P, then exponential dt. You put the value of exponential dt we found to be the whole of that matrix. You substitute, then P inverse. So P inverse we found to be this matrix here. So we've substituted all the three matrices. So this is now what we need to work out. How do we now solve this matrix? You start by solving the first two. So remember, the first two is starting from there and ending here. We solve that first of all. So for you to solve that, you multiply those two matrices. You will get, open, we will have our first matrix there, which is a 2 by 2 matrix. So that will be the solution of the first two. When you multiply those first two, you don't change the order matrix. Then the last part, this matrix remains where it is, like that. So you start multiplying first row times first column. So when you have, that is the first row, then we are going to multiply it with the first column. So the first row times the first column will get 1 times exponential negative 1t. That is 1 times exponential negative t, because you know negative 1 is silent, so it is negative t. So 1 first member times first member, 1 times exponential negative t. You will just remain with that exponential negative t, that element, isn't it? Then 1 times 0 is 0, so that is what you have. Then first row times the second column. First row times the second column, that is the second column. What will we get? We'll get this element of first row, second column. So 1 times 0 is 0, then 1 times exponential negative 2t. You will remain with that. You will remain with that exponential negative 2t. Then you go now to row 2, second row times first column. Second row times first column will give you this element of second row first column. So there you'll get negative 1 times exponential negative t. That will just be exponential negative t times 1. That is will be negative exponential negative t times negative 1 will be negative exponential negative t. You are done with that. Then second row, second column, you'll get that element of second row, second column. Negative 1 times 0 is 0. Negative 2 times exponential negative 2t, you will get negative 2 exponential negative 2. You'll get negative 2 exponential negative 2t. That means when you are multiplying that row with that column, that is what you end up with. So you see, this was outside there. So if we multiply these first two matrices, when you multiply those first two matrices, you end up with that matrix. So after that, we now go to the next step. We are now multiplying the remaining two matrices. So the remaining two matrices we have, that matrix times this, what do we get? That will be equals to the 2 by 2 matrix. So start multiplying first row times first column. If you multiply the first row times that first column. So if you multiply that first row with first column, we'll have exponential negative t times 2. You'll get a member of first row, first column, that element. So exponential negative t times 2. This exponential negative t times 2, you'll get 2 exponential negative t. Then it is plus the second member, exponential negative 2t times negative 1. That will be negative exponential raised to power negative 2t. So positive into negative, that one will be negative. This exponential negative 2t times negative 1, you get negative that. So you found the element of the first row, first column. Then we are still in the first row times the second column. So there we'll have exponential negative t times 1. That will just be exponential raised to negative t. Then plus, second member is exponential negative 2t times negative 1. You'll get negative exponential raised to power negative 2t. You are done with that. Then we now move to the second row times first column. Then we get this element of second row, first column. So the first part, exponential negative t times 2, you get 2 exponential negative t. Then it is plus negative 2 exponential negative 2t times negative 1. Negative 2 times negative 1 is positive 2. So we'll get plus 2 exponential negative 2t. So if you multiply this row and this column, you get 2 times exponential negative t to be 2 exponential negative t. Then negative 2 exponential negative 2t times negative 1, you get positive 2 exponential negative 2t. We are done with that. Then we are now going to the element of the second row times the second column, meaning we get that element. So what is that element? Exponential negative t times 1. You just get exponential raised to power negative t. Then negative 2 exponential negative 2t times negative 1, you get positive 1. You'll get positive 1 exponential raised to power negative 2t, like that. So after that, you've multiplied everything and you have found the transition matrix, which was as required, the Q of t. So this is the transition state matrix. And remember, when you are looking for this part, when you are looking for the second part of this equation, the second part was you determine this Q of t at t is equals to 0. So what is Q of t at t is equals to 0? So Q of t at t is equals to 0. You come and write the whole of this is what you found to be the Q of t. So what have you found? You found the Q of t, the phi variant of t to be that. So when t is 0, it means anywhere you see t, you put 0. Anywhere you see t, you put 0. So negative 0 is just 0. Negative 0 is just 0. T is 0. 0 times anything is 0. 0 times anything is 0. 0. Anywhere you see t, you put 0. 0 times everything there will go to will go to 0, will go to 0, will go to 0. And remember, anything raised to power 0 is 1. So it means this exponential raised to power 0 is 1. The exponential raised to power 0 is 1. 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 Exponential. Look at this multiplication here. When you are multiplying second row and second column, it was negative exponential t times 1 was going to be negative. This was going to be, there's a multiplication we messed out here. That was going to be negative exponential t. That one, then negative 2 exponential times negative 1 was going to be positive 2. I think that mistake we made there. So correct that. Then here, second row times second column, you had negative exponential t times 2 was going to be negative 2 exponential negative t. Then negative 2 times this was going to be positive 2. Correct that mistake. So if you correct that mistake, you can see first row times first column, second row times first column, you get this element. Negative exponential t times 2 is negative 2 exponential negative t. Then negative 2 exponential negative 2 times negative 1, you get positive. That was the transition matrix. So this is exactly what we ought to have had here. I hope you've seen that error we made. So when t is 0, anywhere you see t, you substitute with 0. So 0 times everything goes to 0. 0 goes to 0, goes to 0. That goes to 0, 0, 0. So exponential raised to power 0 is 1, meaning 2 times 1, you just remain with 2. Exponential raised to power 0 is 1. 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 Exponential. This exponential raised to power 0 is 1 times that negative, you remain with the negative 1. Exponential raised to power 0 is 1, you remain with the 2 there. So this is the matrix we have to be the Q of 0 when t is 0. Now if you look at this matrix, it must always be an identity matrix. If it is not an identity matrix, then it means you made a mistake somewhere. You go and check the mistake and you correct. That is why we went back and we checked where we made the mistake and we have corrected in that matrix. Because the matrix you are getting here must be identity. 2 minus 1 is 1. 1 minus 1 is 0. Negative 2 plus 2 is 0. Negative 1 plus 2 is 1. So it means when you are not getting Q, when it is 0 to be an identity matrix, meaning you made a mistake when you are multiplying matrices, you go and check where the mistake is and you correct that mistake accordingly. That is exactly what we've done. We've come back and we've corrected the mistake. Remember when we were correcting the mistake, we had when you are multiplying the second row times the first column, that part, you are going to get negative exponential negative t times 2. You got negative 2 exponential negative t. Then negative 2 exponential negative 2t times negative 1. You get negative times negative is positive 2 exponential negative 2t. We corrected that. Then we multiplied again the second row times second column to get this member, where we found negative exponential negative t times 1 is negative exponential negative t, then plus negative 2 exponential negative 2t times negative 1 is positive 2 exponential negative 2t. And after correcting that mistake, we've actually found an identity matrix, meaning this transition matrix we found is correct. And that is how to handle such cases without using Laplace transform. So it is very, very simple. I made it long because of explanation purposes. What you will need are these 3 matrices only: the matrix P of eigenvectors and its inverse and the exponential dt. Those 3 matrices are enough to give you the transition matrix QT, as you've seen in all the steps we followed. Thank you for watching. See you again next time.